Today we're discussing hypothesis testing, Chapter 9. This is the art of decision making. The researcher begins his study with a hypothesis statement about a population and variables of interest, either qualitative or quantitative. The hypothesis achieves one of the following possible decisions. It can be a comparison problem, compares the sample statistic against the population parameter defined. It can be a validity statement, compares the claims of a company from a sample of products of the company, like the Consumer Reports process. Or finally, it can be a scientific problem, a theoretical problem that tests current conditions of the population against experimental results of the sample. Drug testing is one such example. So a hypothesis test is like a trial. The purpose of a hypothesis test is to determine how likely it is that the null hypothesis is true. The idea behind a hypothesis test is similar to a criminal trial. At the beginning of a trial, the defendant is assumed to be innocent. Then evidence is presented. If the evidence strongly indicates that the defendant is guilty, we abandon the assumption of innocence and conclude the defendant is guilty. In a hypothesis test, the null hypothesis is like the defendant in a criminal trial. At the start of the hypothesis, we assume that the hypothesis is true. Then we look at the evidence, which comes from the data that has been collected. If the data strongly indicate that the null hypothesis is false, we abandon our assumption that it is true and believe the alternative hypothesis instead. This is referred to as rejecting the null hypothesis. So we decide if the null hypothesis is true from looking at the evidence. So at the beginning of the process, in setting up the hypothesis, it depends on the type of decision that is to be made regarding the population and the type of variable that is being studied. The researcher has three choices in setting up a hypothesis, and this, of course, the one in the bottom, is for a quantitative variable. So the following table shows the hypothesis test for the quantitative variable. So in the two-tailed test, here's the two-tailed test that we're looking at. H naught, mu is assumed to be true, and then the alternative hypothesis is that mu does not equal mu naught. In a left-tailed test, the sample mean is less than the parameter. So here we're testing that the sample mean is less than the parameter. And finally, in the right-tailed test, the sample mean is greater than the parameter. So this slide goes over some of the hypothesis terminology. We represent the null hypothesis, the initial state of the population parameter to be tested, to be H naught. The alternative hypothesis, based on the sample taken, the statistics show that the conditions of the population parameter is changed. This is H1. The test statistic is the statistical equation that shows how many standard errors the statistic is from the population parameter is based on initial conditions. And this is from the sampling distribution. And in this case, for a quantitative variable, it's either a z-test or a t-test. The p-value is the probability of the test statistic given the initial conditions of the population parameter. So we're looking at the probability of the event x bar being away from mu under the sampling distribution. Then the decision rule is to reject the null hypothesis based on the p-value. There are, of course, trade-offs when we do the test. Type 1 error is the probability of rejecting the null hypothesis when the null hypothesis is true. This is called the significance level, and usually it is 0.05. We will talk a little bit more about that later. A type 2 error is the probability of accepting the null hypothesis when it's false. So the lower you make a type 1 error, the higher the type 2 error could possibly be. This is the process of testing a quantitative variable. So the assumptions are known to be the population parameter to be tested as mu. We know what mu is that we're testing from previous studies. Data are obtained from a valid sampling method. And then underlying population is normal for the sample size less than 30. So here we have to do box plots and look for skewing ideas. So you can go into your book and look at setting up the testing conditions for a decision. It's on page 419 for the z-test, and it's 434 for the t-test. So we have a t-test. The population standard deviation is known. That is a major idea. Standard deviation is known for the z-test. For the t-test, it's an unknown population standard deviation, right? So that's our t-test. So our test statistics, right, for z, as you can see, we have the z-test statistic is nothing more than our z-score. Z is equal to x bar minus mu naught divided by sigma divided by the square root of n. Right, our usual z-test, and then we look up from the z-test, we go back to our standard normal curve to look up probabilities, right? So we'll be coming here and going to get a p-value. Also, if we don't know the population standard deviation, we have to go to a t-test, and here t is equal to x bar minus mu naught divided by s divided by the square root of n. And again, from our t-distribution, we'll be looking for a p-value, and that's the probability of x bar being away from mu naught under believing that mu naught is true, right? And depending upon whether or not the p-value is, if the p-value is less than alpha, we reject H naught. So that's going to be our decision point. So we have four major processes in setting up a hypothesis test. Setting up a hypothesis, typically we have H naught is equal such that mu is equal to mu naught. So that is our hypothesis initial condition. Then we have the alternative hypothesis, right? We could have mu is not equal to mu naught. That's the two-tailed test. We could have mu greater than mu naught, which is the right-hand test, right? Or we can have H1, the alternative, to be less than mu naught. So it depends on the question being asked, how we will set up the hypothesis test. Once we set up the hypothesis test, we take our data, right? we calculate x bar, and if we know what sigma is, so once we know what sigma is and we know what mu is and we know what n is, we calculate x bar, we know what n is, we can calculate z, and once we get a z value, we will go to step 3, is finding the p-value. Again, if we don't know sigma, we have to calculate both x bar and sx from the population. We get what's called a t-value. And again, we go to finding the p-value from the test. So from the test, z or t, we go to the probability table, which is the standard normal curve or the t distribution. And if this is mu naught, we look at where x bar is in relation to mu naught, and we calculate the probability based on the z or the t. This probability is the p-value, right? And if the p-value is less than 5%, we typically reject the null hypothesis. So the significance of that, the significance value, or we should say the significance value alpha equals 0.05, if the p-value is less than 0.05, we reject usually. And of course, we can set up alpha any way we wish to do so. So here's an example of a quantitative problem. An acid rain in 1990, the mean level of pH in the water of Pierce County, Washington was 5.03. A biologist wants to test the current conditions of the water acidity levels to see if the level increased. A sample of 19 specimens were taken in 2004. Here is the data table, right? And so we would enter that into our calculator. The question is there reason to believe that the acidity in the water has increased? So the idea is we'll enter this into the TI 83, 84, the data set, and then we'll go over to test. So here we've done some of the calculations, but since n is less than 30, we must check for normality, and so we do a box plot, right? There are no outliers, so we assume normality exists for this data set. We set up the hypothesis. Here's the hypothesis. This should be 1, right? So we're checking to see if the pH level is less than 5.03. In this case, we don't know the population standard deviation, so we had to do the calculations on our calculator. So we go over to the t-test. It calculates a mean value of 4.81 and a standard deviation of 0.171. We had 19 values, so we go ahead and put it in t, and we get a negative 5.61. Now on our calculator we get a p-value. We couldn't really look this up on our table, so we would really have to use our TI 83 or 84. Here the p-value is 1.29 e minus 5. That means it's 1.29 times 10 to the minus 5th. That's a very small number. And our significance level is at 1%. So the p-value is much less than 1%. So we reject H naught. So now we're going to be looking at a qualitative variable, right? These are all usually binomial variables. There are some assumptions for using the test statistic, the z-test statistic. Those assumptions are a known initial condition for P in the population, data collected through a valid sampling method, which is simple random sampling. NP has to be greater than 10, and 1 minus P times N has to be greater than 10. Here are the potential hypothesis statements, and you can look at that on page 448 of your book. Right, here is the initial condition, right, that P is equal to P naught, and then we have the three possibilities. P doesn't equal P naught, P is greater than P naught, or P is less than P naught. Then, of course, we set up our test statistic, Z, right, and here is P hat, right, remember what P hat is. It's x over n, where x is equal to the variable, the number of individuals that have the characteristic, and n is the sample size. Then we calculate the rest of the information in the z-test. We do a z, and then we calculate a p-value, just like we did in the quantitative problem. And then we check to see if we reject H naught if the p-value is less than some significant level. So we put the p-value on the probability curve, and if it's less than, if that probability is less than the significance level, we would reject H naught. So here is a quantitative problem. The drug Lipitor is meant to reduce cholesterol and LDL cholesterol. In a clinical trial, 19 out of 863 patients taking 10 milligrams of Lipitor daily complain of flu-like symptoms. Is there sufficient evidence to conclude that more than 1.9% of the Lipitor users experience flu-like symptoms as a side effect? Test at a significant level of 0.01, right? So the first step is, do we meet the assumptions, right? And in this case, we do. We know that P hat is 19 over 83, right? So that's 0.19. And then we also get a the standard error is 0.005, and we set up the hypothesis test. So here's the hypothesis test. We're looking to see, based on the question, is there evidence to conclude that more than 1.9% of the Lipitor users experience flu-like symptoms, and so that's how we get our hypothesis test. Now we do the test statistic. Here is our test statistic, right? We do the calculation. We get a p-value of 0.2743, and the decision is, since we are not less than 1%, we do not reject H naught. So our conclusion statement is, there's not enough evidence to conclude that the percentage of Lipitor users are not greater than 1.9%, stating that they have flu-like symptoms. So that's the conclusion of hypothesis testing briefly. We will be looking at doing some problems online, some more videos so that you can work the problems on exam 3. and also work some problems in the book. So we'll be going over some of those issues, and we'll be putting that video together.